All right, we're going to look at two sample problems that hopefully will help you better understand how heat engines work. And number two, will better explain the difference between the Carnot or the maximum efficiency and what is called the actual efficiency. All right, in the first problem, it says, an engineer designs an engine that can reach a high temperature of 580 degrees Celsius and can be cooled to 320 Celsius. What is the Carnot efficiency possible for this engine? All right, so first of all, Carnot efficiencies are based on Kelvin temperatures. So the first thing I'm going to do is add 273 to each of my Celsius temperatures so that I turn them into Kelvin. So this will be 853 Kelvin, and 320 is going to be 593 Kelvin. All right, the next thing I'm going to do is I'm going to draw myself like a little picture to better represent my engine. So a heat engine is designed on the principle that you have a hot area, 853 K, and I have an area that can be cooled down to 593 K. And because I have different temperature regions, heat is going to naturally flow. I'll build myself a little mechanical engine or something that is going to extract this heat flow and turn it into useful work. And the useful work in this sense would be being able to drive my car. So I like burn my gasoline, and then I drive my car, and then I have some exhaust. So if I was an engineer and I said to my boss, I can get the gas temperature like up to 853 K. And then somebody else says, oh, well, I know how to build an exhaust system and I can get it to cool down to 593 K. So then we could calculate the maximum possible efficiency of this engine. And that is called the Carnot efficiency. So I'll put a little C down here for Carnot. And that is literally the difference between the temperatures, the temperature high minus the temperature low divided by the temperature high. So the Carnot efficiency is going to be 853 minus 593 over 853. And when you divide that out, it's going to turn out to be 0.305. And then I multiply that by 100, and then I can report its efficiency as 30.5% maximum efficiency. And then if your boss says, well, that engine's not good enough, the only way that you can make the engine better is this engineer has to go back and somehow get that gasoline chamber higher temperature, or the coolant guy has to go back and he's got to work on the exhaust system to get it to go lower. But by maximizing the temperature difference between the two, you can increase the theoretical maximum efficiency of a car engine. All right, and then in the next problem, we're going to take this engine that has a maximum efficiency of 30.5, and we're going to put it in a car and see what we get. Just because it has a theoretical efficiency of 30.5 doesn't mean that's what you're going to get. So this then is going to be called the actual efficiency. What am I really going to get? So when you look at the actual efficiency, you're not focusing on temperature like we were up here. We're instead focusing on Q, on heat, and heat is measured in joules. All right, so the engine above is then put into a vehicle. The vehicle was able to do 4,000 joules of useful work. So there was this heat flow that was happening. I had my engine, and I was able to get a work of 4,000 joules out of this engine for a period of time, while during that same period of time, 12,000 joules of heat was expelled. So that must have come out of the gas or the exhaust system. So draw a model of this engine. I'm doing that. Letter B, calculate the energy that must have come into the higher temperature chamber. So yeah, I had gasoline burning in my high temperature chamber. And so if I kind of think to myself, in the high temperature chamber, those joules, that heat has to be divided into the work joules that I get and then the garbage joules, the exhaust joules that I get. And so if I have 4,000 plus 12,000, I must have had 16,000 joules at the start of the story. And burning my gasoline, those calories in the gasoline, must have converted into 16,000 joules. All right, determine the actual efficiency then of the engine that has a maximum efficiency of this. So to determine the actual efficiency, I'll say efficiency this time, instead of focusing on the differences between the temperatures, it's going to be the differences in the Q values over Q high. So I had 16,000 come in. I had 12,000, I'll say wasted, over the 16,000. And so I divide that out and I find out that I get 0.25. So I was able to get 25% efficiency out of this engine. Now you can see that it had a theoretical efficiency of 30.5. So out of the 16,000, I sure wasted a lot of joules. Maybe I have to tweak my engine here a little bit so that I can maybe get this up to 5,000, and then maybe this is only 11,000 and I'm wasting less joules. So surprisingly, in a real car engine, and when you burn your gasoline, we waste a lot of that heat coming out of the exhaust. And if you put your hand near the exhaust pipe of your car, you'll notice it's hot, hot, hot. And the more joules that we can extract to go into the W, the less that are going into here, and we can maybe get this closer to its maximum efficiency.